In the previous video, we learned how to find relative max, relative min, absolute max, absolute min. These are called extreme values. In this video, we will deal with some applications of maxima and minima. Maxima means maximum values and minima means minimum values. Now, finding maximum values or absolute max, relative max, absolute min, relative min, this process is called optimization. So this is called optimization. So by optimization we mean the process of finding extreme values. So optimization deals with, for examples like lowest cost, this is minimum, or greatest possible profit, this is a maximum problem, and so on. So if we read in the question maximum or greatest, largest, smallest, lowest, all these mean that we have optimization problem. And we learned some applications of the first derivative. So the first derivative of the function, I mean f prime of x, can tell us what are the critical points and the intervals where the function is increasing and the intervals where the function is decreasing. The derivative can also tell us how to find local, or what are the local max or relative max and relative min. So all these things can be obtained from the first derivative. So let's start with the following application. A clothing company manufactures expensive hockey jerseys for sale to university bookstores in runs of up to 500. Its cost in dollars for a run of X hockey jerseys is C of X. So we are given the cost function here, where X represents number of hockey jerseys. The question is how many jerseys, I mean the value of X, should the company produce per run to minimize. This is a key word, minimize. When we read to minimize, that means we have optimization problem. We want to minimize which function? We want to minimize the cost, the average cost. So the problem is minimization problem, which is optimization problem, and we want to minimize the average cost, not the cost. We are given the cost function here, but we want to minimize the average cost. Now, how to deal with this problem? The first step to tackle this problem is to define the variable x. So the first step is to define the variable x. X is number of hockey jerseys that should be produced per run. And then we determine, this is the variable. Then the second step is to determine the objective function. What is the objective function? The objective function is the function that we want to maximize or minimize. So the objective function in this case is the cost, the average cost. The average cost is denoted as C bar of X, and it's equal to the cost function divided by X, the quantity. So this is equal to, now c of x is given, so it's 2000 over x. We divide each term by x, 10x over x plus 0.2x squared over x. Now we simplify, so c bar of x is 2000 over x plus 10 plus 0.2x. Now we have the function that we want to minimize. Minimize this function. Okay. In this case, we need to determine the domain. So we have some constraints on x. So we need to determine the domain of application, or the applicable domain. So we have some constraints on x, on the variable x. So we should determine this domain. So from the problem we find that we want to have up to 500. So the quantity, the maximum value of the quantity is 500. So x is less than or equal to 500, and for sure it's greater than 0. Or we can write it as an interval 0, 500. Now we start the minimization process. How to minimize it? Now we find the derivative first. So the derivative of the function is, what is the derivative of this expression here, or this term, 2000 over x? The derivative is, let's apply the quotient rule. So the denominator is x times derivative of the numerator, it's 0 because 2000 is constant, minus the numerator 2000 times derivative of the denominator, derivative of x is 1, over x squared, the denominator squared. This is 0, so we get negative 2000 over x squared. Now what is derivative of 10? It's 0. What is derivative of 0.2x? It's just 0.2. Now we find critical points. So derivative here and critical point. How to find critical point? We set this equal to 0. So c bar x equal to 0, or c bar prime of x is undefined. Now let's start with the first case. Can this be equal to 0? So let's set this equal to 0 here. Negative 2000 over x squared plus 0.2 equal to 0, and then we solve for x. So let's bring this to the right hand side. We get negative 2000 over x squared equals negative 0.2, and then we multiply this by this. Negative 2000 equals negative 0.2 x squared, and then we divide by the coefficient of x squared. So divide by negative 0.2, negative 0.2, we get x squared equals 10,000. That means x equals 100. Now what is the value that makes the derivative undefined? That value is x equals 0. But since x equals 0 does not belong to the domain, this does not belong to the domain. The domain is x. X can take values from 0 to 500. 500 is included, but 0 is not included. As we can see here, we don't have equality. No equality here. So 0 is not included, so we just cancel this critical point. We only have one critical point in this domain. Now we start studying this. We start studying the sign of the derivative of the cost function c bar prime. So we put the critical point here, it's 100, and the domain is 0, it's open at 0, to 500, it's closed at 500. Now we study the sign. So the sign can be determined by choosing some value greater than 100. Let's choose 200 as a test value, and let's choose a value between less than 100 and greater than 0. Let's choose 1. So if we substitute 200 into c bar here, we get a negative, we get a positive value. So this gives positive value. You can substitute or plug this value here into this formula c bar prime, you get a positive value. If you substitute 1, you get negative value. So this is decreasing here, increasing here. That means 100 is a minimum value. So now we find the point. So we have 100 and c bar of 100, the image or the value of the function c bar at 100. So c bar of 100, we just substitute 100 here into c bar. So substitute 100, you get 2000 over 100 plus 10 plus 0.2 times 100. And then using a calculator, if you want to do the calculations by hand, you get 30 plus 20, and that's 50. So this value here is 50. So when this is x, and this is x, and this is c bar of x. So when x equals 100, we get the average cost equal to $50 per jersey. So that means the company should produce 100 jerseys per run for the lowest possible average cost of $50 per jersey. So that's the conclusion. So we can write the conclusion here. The company, this is the conclusion, the company should produce 100 jerseys per run for the lowest possible average cost of $50 per jersey. Okay. Now let's take another example. The second example here is that Muna wants to build a rectangular enclosure of her pet rabbit against the side of her house. She has bought 100 feet of fencing. What are the dimensions? What are the dimensions of the largest area that she can enclose? So here we have some keywords. The first keyword is that we want to find dimensions. What are the dimensions? Length and width, for example. So x and y, we have two variables because this is rectangular. This is rectangular enclosure. And we have a keyword here, largest. That means we have optimization problem. Optimization problem. It's maximum problem. and we are talking about area. That means this is the objective function, because the objective function is the function that we want to maximize or minimize, optimize. So here we want to find the dimensions that give the largest area, the largest possible area. Okay, now let's graph this, or visualize this problem by graphing the fencing and the enclosure. We have a rabbit here, and this is this is a wall of the house, and here we have, this is the fencing. Okay, so the shape is rectangular. Shape is rectangular. Let's call this dimension x and this dimension y. So first we define variables. We have two variables, x and y. And then the objective function. What is the objective function? The objective function is the area function. The area of this is a, let's denote it as a, equals the width times length. So x times y. So this is the area of the enclosure. Now in order to solve this problem, problem is different from the previous problem. The previous problem, we have a function that depends on only one variable, the variable x. As you can see here, it's x. But here we have two variables. We can't minimize in this case using the tools that we learned in this section. So we have to need to reduce number of variables to one variable. How can we do this? We need, in order to reduce this number into one, we need an auxiliary equation that can help us to reduce this number of variables. So what is the auxiliary equation? If we back to the question, we have a fencing of length 100, and that fencing should cover this side, and this side, three sides. So the sum of the three sides should be 100, the length of the fencing. So 100 equals, we have 1x but 2y, this y and the corresponding one, because we have rectangular shape. So we have x, 1x, because the other x here this is part of the wall, that's part of the house. So we solve this for x or for y, you have the choice. But for me, I may prefer to solve for y in order to write this function in terms of x, and that's the familiar variable. But it's easier to solve this for x and write this function in terms of y, but I'm not gonna do that. I will solve for y to write the function, the objective function, in terms of the variable x, because we are familiar with that variable. So we solve for y. So we subtract x from both sides. We get 2y equals 100 minus x, and then we divide by both sides by 2. So we get y equals 50 minus x over 2, or 1/2 x. So this is the auxiliary equation. We substitute it here to write the function a in terms of one variable x. So this is x times y, but y is 50 minus 1/2 x. Those are equivalent. You can write x over 2 or 1/2 x. Those are the same thing. Okay, now we have one variable. Let's simplify more. X times 50, 50x, minus x times 1/2 x, it's half x squared. Now we have a function of one variable. We apply now the optimization, or we find the relative values. So let's find extreme values. Let's find the derivative first. So we have 50 minus x, because when we differentiate this is negative 1/2 times derivative of x squared is 2x. We cancel 2, we get negative x. Now we want to find critical values, so derivative, then we find critical points. So we set this equal to 0, and that means 50 minus x equals 0. We solve for x equals 50. Now the second case is that a prime of x is undefined, but this is not true. It's defined everywhere because this is polynomial. We don't have a denominator variable in denominator, so to worry about that, or we don't have any problem with this function. Okay, so that means we don't need to worry about the derivative where the derivative is undefined, because it's defined everywhere. Now, so the point is x equals 50. This is the critical point. Now, what is the domain? The domain of the variables x and y should be greater than or equal to 0, because these represent lengths. The length should be non-negative. Now we draw the number line, or we make a sign chart for a prime of x. So sign chart, and we have the critical point here, x equals 50. Now we study the sign of a prime. A prime is this function. So when we choose a value greater than 50, like 60, and substitute it here, plug it into a prime, we get negative value. And when we choose a value less than 50, like 1, and plug it into a prime, we get positive value. So this is increasing the function, the area function a is increasing here and decreasing here. That means this point is maximum, as you can see here. This is maximum. So this is relative maximum, or this should be on this domain. This is the domain is 0. I should write here 0. So this is relative maximum, and then we found that we have 50 and a of 50. Now 50, and what is a of 50? We need to substitute into the formula for a of x. So substitute 50, you get, after substituting 50 here, we get 50 times 50 minus 1/2 50 squared. Now simplifying this, okay, so we are looking for the dimensions. We don't want to find the value of the area now. We can find it later, but we want to find dimensions, because the question is about dimensions here. So we want to find x and y. That makes the area maximum, and then you can use this to find the maximum area. So this should give us the maximum area. You can compute it. This is the maximum area, which happens when x equals 50. Now the dimensions are x and y. So x is 50. Now what is y? Now y from the auxiliary equation star, y equals 50 minus 50 over 2, and that gives us 25. So the values are x equals 50 and y equals 25. When x equals 50 and y equals 25, we get the dimensions that give us the largest area. They give the largest area. If we want to compute the largest area, we need to do these calculations. Okay, but the question is just about the dimensions. Okay, now another example, or the last example in this video, is the following. A company built baby strollers. It estimates that it sets the price of a stroller at P dollars. So this is a price function. Then it can sell Q equals 300,000 minus 10p squared strollers per year. That means this is the quantity. Q is the quantity. And this is the price. P is the price. Now the question is, what price will bring, what price we want to find P that will bring in the greatest, that means maximum problem, the greatest annual revenue. That means this is the objective function. The objective function is the revenue function. So let's start by defining variables. The variables are Q, which represents number of strollers. This is the quantity. And P, which represents the price in dollars. And then we define the objective function. What is the objective function? If we know the quantity and the price, the objective function is the revenue function, but the revenue is, we know that revenue is the price times the quantity, or quantity times price. The price is P, quantity is Q, so this is R. R, the function R is P times Q. But as you can see, we have two variables here, two variables, P and Q. So we need to get rid of one of them. So we need to reduce, to write one of them in terms of the other. So we need to reduce number of variables to one, just one variable. Okay, so how can we do this? This is very simple, because we are given Q. This is given in the problem. So the revenue can be written in terms of the function P. So, and that's what we want to find. We want to find P that gives the greatest revenue. So R equals P times Q. Q is 300,000 minus 10p squared. So the revenue equals 300,000 P minus 10p Q. So this is the function that we want to maximize. Okay. Now, what about the domain? The domain is Q, which represents number of strollers, should be greater than or equal to 0. It can't be negative. Now, what about P? Now, for P, we need to solve this. We want 300,000 minus 10p squared to be greater than or equal to 0, because this is a q. This is q. Is it greater than or equal to 0? I just replace it with this expression. And then we solve for p to find the domain for p. So let's bring this to the right hand side. This becomes 300,000 is greater than or equal to 10p squared, and then we divide both sides by the coefficient of p squared. So we get p squared is less than or equal to 30,000. P squared, and then we take square root of this. That means we can solve it as an equation. So we have p squared equals 30,000, and then p equals plus or minus square root 30,000. So we have plus or minus, if you use the calculator you find that, or you want to simplify, you get 100 square root 3 plus or minus. So p is between those two values, between negative 100 square root 3 and positive 100 square root 3. So p is between these two values. So the domain is p from negative 100 square root 3 to 100 square root 3. Okay, now this is the domain. This is the value of p, the domain for p. This is the domain for q. Okay, now let's start maximizing the problem. So we need to find the derivative of the objective function. This is the objective function. So we find r prime of p. R prime of p, because it depends on p, only p. It's 300,000, because derivative of 300,000 p is just 300,000, minus 30p squared, because derivative of 10p cubed, 10 is a constant, derivative of p cubed is 3p squared, and that is 30p cubed, p squared. Okay, so this is r prime. Now we set this equal to 0, and then solve for p to find the critical point. Derivative, and then critical point. So 300,000 minus 30p squared equal to 0, and then we bring this to the right hand side. We get 300,000 equals 30p squared, and then we divide both sides by the coefficient of p squared. Divide by 30, you get p squared equals 10,000, and that means p is square root of 10,000, and that is 100. So that's the value of p that maximize the revenue. So we have p and r of p. So this is the point. P is 100 and r of 100. We substitute it into the revenue. Okay, but before this, let's study the sign of the derivative, sign chart, because we want to make sure that this maximizes the function, the revenue. So we put here r prime, and we have 100 here, and the p is between negative 100 square root 3 to 100 square root 3. Now we can study the sign. Let's choose a value between 100 and 100 square root 30 square root 3. So if we substitute some value here, like 100 square root 2, we get a positive value. You can calculate this using using calculator. So just substitute it into R prime. R prime becomes 300,000 minus 30 times 100 square root 2 squared. And that's 300,000 minus 30 times 20,000, and then 300,000 minus, we have 5 zeros here, 6. So 300,000 minus 600,000, this gives us negative sign. Okay, or you can use the calculator, that will give you the value, and then you can determine whether it's positive or negative. And then you substitute a value here like negative 100 square root 2, you get positive value. So here the function is increasing, here decreasing. That means this is a maximum. So this is P, that gives us maximum revenue. So when P is, the price is $100, then we get revenue equals here 300,000 times 100 P minus 10 P cube. So I should write 10 times 100 cube. Then using the calculator you can find that this is 20 or 20 million. So this is the revenue obtained when the price is $100.